I'm Shaun Marcott. I'm a new professor at the University of Wisconsin-Madison. And my talk today is mostly going to comprise of what I did for my PhD and a little bit of what I did for my postdoc while I was at Oregon State University. And the title of my talk is, what have the last 21,000 years told us, or what is it telling us about present and future climate change? And so really what I'm going to do is I'm going to give you, what I'm going to try to do is to give you a geologic perspective on what's happening with climate change, CO2 emissions, and then and what's going to happen in the future. So this is really about how a geologist views, or at least one geologist views, climate change going into the next 200 to 10,000 years. Right, so the other thing I wanted to do was just sort of introduce myself, which I thought was useful since I haven't met most of you. So I'm a glacial geologist by training, which means I do a lot of work in the field, trying to understand how glaciers have changed through the geologic past. And because glaciers are intrinsically linked to climate, I'm also interested in climate change as well. I spend the bulk of my time either out in the field during the summer, so doing field work in Greenland. I've been in Antarctica in the western US. And then when I get back home, I spend a lot of time in the lab doing geochemistry using various apparatuses and techniques. And I also work quite a bit with climate modelers to sort of understand the physics of what's going on. I don't do climate modeling, but I find that working with climate modelers provides a more holistic perspective on what's going on with the glaciers and with the climate. So that's who I am. And here is a geologist's perspective on the energy balance of the planet. I think it's appropriate that I have a cartoon here. Looks like it's drawn by a 5-year-old. And really, the energy balance of the planet is primarily controlled by 3 knobs. So one of them is incoming solar radiation, and then the reflectivity of the planet, so the albedo, and then the atmospheric content of the planet itself, so the greenhouse effect. So really it's a budget of what's coming in and what gets to leave, and this is being dictated, what leaves gets dictated by how reflective the planet is over time, and then how much of it gets re-radiated because of the greenhouse gases in the atmosphere. So the greenhouse effect. And today we're disrupting this balance, or a way you could disrupt this balance is you can change any one of these knobs at any given time, and it's going to change the radiative balance of the planet. So for instance, if you change the way we orbit around the sun, which we know has happened in the past, you're going to change the energy input into the planet, and that's either going to cool or warm the planet. So Jin-Ho talked about the ice age cycles, and we know that those these 100,000 years, even 40,000 exist in how we orbit around the sun. You can also change the atmospheric albedo or the surface albedo of the planet, so how much gets reflected back into space. Either through volcanoes or in the size and distribution of ice on the planet. And then the other one we know quite a bit about is if you increase the amount of greenhouse gases in the planet, you're going to warm the planet just because you're going to absorb more of the sun's energy. And this is the one that we're changing quite a bit today. So we're playing with this knob quite a bit by sticking a lot of CO2, nitrous oxide, and methane and other greenhouse gases into the atmosphere. And essentially it's causing what we know is global warming. So this is going from the year 1850 here to present to the year 2000, and these are the temperature anomalies over this time period referenced to roughly the 1960s and 1980s. And you can dice this up any way you like. This is annual average temperatures here, so you can see this long-term warming beginning at about 1900, or you can break it up into decades if you like to look at it like that. And so here are the projections for the future, or at least for the next 300 years, or 200 years. And this is generally how this question gets couched, is what's happening today and what's going to happen out to 2100, or even if you're really thinking long term, you go out to about 2300. So these are This is what's observed. So this is the radiative forcing. This isn't CO2, but this is all the greenhouse gases slammed together and described as radiative forcing, but essentially it's being driven by CO2. So this is the observed, and then these are the potential emission scenarios that we might follow depending on how much carbon we put into the atmosphere. So this is the emissions, and then these are the temperature projections based on these emissions. So this plot comes from the IPCC, the most recent IPCC report. So you can see if we take this high projection here, or this high emission scenario, you're going to get a lot of temperature change over the next 200 years, something like 6 degrees Celsius change. But really, if you want to think of this as a geologist, 200 years is nothing. That's not even like a blink of an eye in geologic time. In fact, this isn't even a blink of an eye in geologic time, but this is the way I'll frame it. So this is what the last 100 years look like, and what some of these projections out to 2,300 years look like. But thinking of it in the last 20,000 years and then 10,000 in the future. And you can see it's just a little line here. And the question is, what's going on back here? Is this anomalous? Maybe in the past this isn't anomalous. Maybe CO2's been jumping up and down. We sort of know this answer because Jinho already revealed it, but the other question is, what has global temperature done over this time period, and what have the rates been? So this is the way I'm going to frame this, and I'm going to sort of build this plot for you to sort of think about and give you some perspective of how I think about climate change today. So the question is, which I've already said, is climate change today anomalous? And then also, we only have 100 years worth of data, and one thing the geologic record can provide us is how has climate changed at the 100-year, 1,000-year time scale, or depending if you like to work in deeper time, million-year time scale, or billion-year time scale. That's what the geologic record really allows us to start thinking about. Because the instrumental record is, we only have 100 years worth of data. So we have to find some other way of understanding how the climate system works, and we have to go to geology to do that. So how do we do that? We use, and Aradna already pointed this out, is we use a number of different archives to get at this answer. So for the last 1,000 years, we primarily use things like tree rings. Corals provide an excellent record of what's going on in the ocean, borehole temperatures, ice cores, and lake sediments. And what they've told us over the last 1,000 years is this. So this is temperature change, again expressed as an anomaly. This is from Michael Mann's work in 2003 from GRL paper. And this is temperature going back, so this is today, and this is going back about 2,000 years into the past. So what you basically are getting here is you're getting temperatures over at least the last 1,000 to 1,500 years have been generally flat. There is some variability. These are a number of different reconstructions of temperature based on a number of different proxies, tree rings, boreholes, etc. But really, and then so it's been generally flat for the last 1,000 years, and then we have this long increase. So this is the global warming that we're seeing today. Most people know this plot by its colloquial name is the hockey stick plot, where you have the shaft here, and then you have the blade where it jumps up. And the hockey stick itself was sort of a lightning rod for a lot of people, and is incited a lot of interest because what it really did, why it was so significant, was it put today's temperatures into some perspective over the last 1,000 years. I mean, that's exactly what it did, is it took today's temperatures and it put it into a longer term perspective. And basically what was concluded was that today's temperatures are warmer than they have been over the last 1,000 years, which was significant. And it really told us something about what's going on today. Now the question is, can we keep going further back in time? And the answer is yes. We can continue to mine the geologic record and build out this information, though at lower resolution. So this data from the last 1,000 years can be built out because it's from tree ring data. It's annually resolved for the most part. But if you want to give up developing an annual record and you are willing to sacrifice more of a centennial millennial scale record, you can go back to about 11,000 years. And this is what I did as part of my PhD that was published in 2013. So this is a global network, these dots here, of the sites that we chose based on data sets that have already been published. to build a global climate change or temperature reconstruction over the last 11,000 years, what's known as the Holocene epoch. And just for reference, these hatch marks here are where all the data sets come from for the last 1,000 years. So what you already notice is that over the last 1,000 years, we've primarily been building this record from the land, whereas for the data sets I'm going to show you, they're built from the ocean, primarily ocean archives, though there are some ice cores and some lake records. But what we find is the exact same thing over the last 1,000 years. So this is going back 2,000 years in the past. Again, this is an anomaly reference to some time period. And the gray here is what was reconstructed from these tree reconstructions, these land-based reconstructions. High resolution. In general, it's flat, though there's a small dip, which is commonly known as the Little Ice Age, and then followed by this increase, at least in the gray record. And what we have is a lower resolution of that, this blue and purple line here. The blue is the one standard deviation, the line is the mean, and we generally get the same result, but at a lower resolution. So this is, this is data sets. The purple here represents data sets from the ocean. The gray here represents data sets from land, but in general, we're getting about the same answer. So based on this, we felt pretty confident about using these archives to reconstruct climate faithfully over the last 11,000 years. And this is what we reconstructed. So this is going now from 11,500 years ago all the way up to present. This is coming out of the last ice age, this warming here. And then you have generally a period where temperatures haven't generally changed, and then followed by this cooling up until about the year 1800. And then from there, this little line here in our data isn't actually robust, but we generally get this cooling trend, and then we know from the instrumental data that this is followed by global warming. The question is today's warming, is today warmer than it has been over the last 11,000 years? And rather looking at it as a time series, I prefer to look at it as a histogram because I think it's more informative. So this is now all that data that I just showed you, just reduced down to a histogram plot. And so temperature here on the x-axis, and then percent of the Holocene. This is just how I chose to normalize it here on the y. So this is the histogram of Holocene temperature data over the last 11,500 years. If I just plot the first decade of the 21st century, it plots right here. And so what we can generally conclude is that, and where this plots is essentially 72% of the Holocene is cooler than this time period, but about 28% of it, at least based on our uncertainties, is warmer. So what we concluded in the paper was that is it warmer today than it has been the last 11,000 years? At least based on our analysis, not quite yet. What I thought was more interesting, though, we can do the same thing for the beginning of the 20th century. So this is the first decade of the 20th century, just plotted as a line here. And what you'll note is that the Holocene tends to be the coolest time period of the Holocene, of the entire Holocene. So one thing we can conclude is that at least going from the year 1900 to the year 2000, we've gone from the cool end of the spectrum in the Holocene to the warmest end of the spectrum, which is pretty interesting. One way I like to think of this is that if you lived over this time period, the last 100 years, is you actually would have experienced the full range of climate variability of the last 11,000 years. Okay, so then the question is, can we keep going? And the answer is yes. Geology just keeps on giving. We use the exact same data sets primarily, and we built out this reconstruction to the last 20,000 years. So this is from a paper from 2012 by a colleague, Jeremy Shakin, who's now at Boston College. We both did our PhDs together at Oregon State. And we used nearly the exact network of data sets to build out this reconstruction out to 20,000 years. And one question, this is following up on what Jin Ho's talked about, that we wanted to investigate, was this relationship between CO2 and Antarctic temperature and global temperature. So one thing we know is one question is, what's the relationship between CO2 and the last natural global warming? So going from the Ice Age, so this is going from 22,000 years ago to 8,000 years ago. This is Antarctic temperature here in red, and this is the CO2 reconstruction in brown here. And one thing we know is that temperatures, at least in Antarctica, tend to lead the CO2 changes in the atmosphere, which is really interesting. And one conclusion is, well, one observation, I shouldn't say conclusion, is temperatures lead CO2 changes, and the conclusion is the initial CO2 rise is caused by this warming in Antarctica. Right? So I just said that this warming is causing this CO2 rise, which is a little counterintuitive. So was Al Gore wrong when he showed this plot where he's showing the CO2 and temperature relationship, and Jin Ho showed the same thing, and so did Aradhana? Is this guy right? Temperatures appear to drive CO2, not vice versa. On this point, Mr. Vice President, you're not just a little off, you're totally wrong. There's something important to remember here. Antarctica is one spot on the map. And when we talk about global temperature, we really need to think of it as global temperature. So this is a surface temperature change plot from a paper by James Hansen, just showing that there is spatial variability in global temperature. Most of the planet is warming, hence global climate change. But there are places across the planet that actually have slightly cooled over this interval, because there is a spatial pattern to what's going on. And not all of this is being caused by CO2. So this is what was sort of the motivation of collecting this global network from across the planet, was we really want to get a global picture of what's going on and not just focus ourselves in Antarctica. And there's a mechanistic reason for doing that. So here's the reconstruction over the last 20,000 years. This is going again from 22,000 to 8,000 years ago. And this is global temperature reflected as an anomaly, in this case from the Holocene. And so this would be the last ice age here. This is what's commonly referred to as the last deglaciation. And then the Holocene epoch, or our current interstadial warm period here. Okay, so let's just compare this now to what I just showed you. So here's our relatively new reconstruction of global temperature over the last ice age and into the current interglacial. Here's Antarctic temperature plotted here. This is from Pernin paper in 2013. And then here's the CO2 reconstruction from Antarctica. And if you just compare the two, Antarctica to CO2, you still get the same answer, which is CO2 changes after Antarctic temperature changes. But the question is, what does global temperature do compared to these other ones? So let's just zoom in here. And what you can see, or one thing that we concluded, is that beginning at about when the deglaciation began, CO2 changes tend to lead Antarctic temperature tends to lead the CO2 changes over the entire glacial period, but the global temperature changes tend to lag the CO2 changes over the same time interval. Except for this little part here, but we do have there is a reason, we do have some ideas of why this little change is occurring, and that probably has to do with our rotation around the sun. So what we concluded was, yes, CO2 changes after Antarctic temperature, but it actually leads the global temperature. So the point is that CO2 is important. I don't think anyone was questioning this, but this is now just a demonstration of that CO2 is important for global average temperature over this time period. Right, and yeah, CO2 is important. I've already said this. And so one other thing to point out is this is an older reconstruction now by Eric Monin from this 2001 paper. And I was involved in collaboration actually with Jin Ho on reconstructing a new high-resolution CO2 reconstruction over the same time period. And we get even a more robust this data set is more robust in terms of chronology, so we are more confident of when these CO2 changes based on this new ice core, and we get the exact same answer. So all the data is essentially showing that Antarctica actually is leading the CO2 changes, but it's the CO2 changes are actually leading the global changes that we see across the planet. And the reason why is that CO2 just doesn't magically appear in the atmosphere. It has to come from somewhere, and we think what's going on is that that it's coming from a reservoir that's been cut off from the atmosphere for a long time in the deep ocean, and where it essentially upwells is in Antarctica. And the way it does that is you have to warm Antarctica to be in. One idea is that you warm Antarctica to draw back sea ice, and then you begin to upwell this reservoir of CO2 into the atmosphere. So you need the local warming to begin to kick the system globally into gear. So this is the idea of feedbacks in the system, where some warming in one part of the planet begins to hit the carbon system in such a way that CO2 begins to go up, and then it begins to start this chain of deglaciation across the world. So here's now our reconstruction of global temperature for the last 10,000 years based on the geologic record, going from the Pleistocene to the Holocene. So this would be the last ice age, the deglacial period, and then this relatively warm period that we've been living in, known as the Holocene epoch. So let's get back to this question, which is, how do I, at least now, after doing all this, how does this look compared to the geologic record? Well, here's the Holocene epoch. This is where modern humans have essentially learned to become a more organized, civilized society. And this is what temperatures looked like over that time period. Here's what CO2 did, and there's the rate of change here on the bottom. And then here's the last deglaciation here, where this is the last ice age, and this is the CO2 levels over that same time period. So this is about a 4-degree change going from about here to there. And depending on the different emission pathways that you choose, that's about this equivalent of what we're expecting to do in the next 200 years. But the difference is rates. This took about 10,000 years to occur. This is going to take somewhere in the neighborhood of 100 to 200 years. So better, the thing I like to look at least is the rate of change over this time period. One other thing to point out is that these changes, if you actually just don't couch it in the terms of the last 200 years, are geologic in scale. They truly are, because of the long life of CO2, or at least its perturbation to the atmosphere, and how much we're actually going to stick into it. So this is a reconstruction from climate model simulations, coupled carbon climate model, where they just ran out these different scenarios out to 10,000 years. So this is work by Michael Evie. It was published in the Journal of Climate. And depending on the different emission pathways that we choose, so this is the amount of carbon that we put into the atmosphere. This would be depleting all of our known resources, and this is something less than that. These are the different pathways you would follow or expect, at least based on this model, in terms of temperature. So really you get this, and the way this model works is it's just a pulse. They put in, all this goes in about 200 years, and then it just stops. And this is what you're left with. You're really talking about a step change here when we go into the future. So really, from my perspective, a geologist's perspective, just talking about this in the last 200 years is really not giving it due diligence. You really need to be thinking about it in the geologic context, where what's going on now will have long-lasting effects for a really long time. And then the way I like to think of it is, what we know about what's gone on the planet really is is a very, very small chunk of time. It's roughly only about 100 to 150 years, and most of that we get from the instrumental data set. And geology really gives us, puts all of what's going on today into some type of context of what's gone on in the past. And physics and modeling is going to give us giving us more information about what this might look like in the future, depending on how we choose to carry on over the next 100, 200 years. Okay, I'll stop there. Thanks.